So over to you, Viraj.
Hi everyone. So it's been 1 year since I started my PhD now, and the topic which I'm going to cover today is mostly the work that I did on my master thesis. So yeah, let's start. So in this talk, I will be talking about mainly uh, inhomogeneous universe models and how the CMB, so the cosmic microwave background temperature anisotropies are affected due to the presence of a large-scale local void with the observer at some distance from the center of the universe. So there are some terms which are not regularly heard about in this sentence that I just spoke. So for example, the center of universe, I mean, we all know that universe doesn't have a center as of the standard model of cosmology today. Uh, but yeah, I will explain in a few slides how why is it called so, and also just to let you know the word local void means that it's just that the observer is that is us is present inside the void region, and I will explain everything the model, the structure of model, and what is it made of, etc., etc., in the next few slides. So let's begin. Uh, okay, so this slide shows the evolution of the universe with a time in the standard model of cosmology. So time or scale factor, we can express it as a function of both. Uh, our universe has been expanding since the Big Bang, that is the birth of universe, we would say. Moreover, it is an established fact that the universe is currently in the state of accelerated expansion. So in the standard cosmology, we postulate the cause for this expansion as an exotic form of energy called the dark energy. So this graph shows the various stages of the evolution. So here, in at until some point, the universe was radiation dominated. So the radiation, that is the electromagnetic radiation, was the major constituent of the universe. Then after some time, it became matter dominated. That is so as I will explain, the so dark matter and the normal ordinary matter were the major constituents, and then after some time it became lambda dominated, which is the dark energy dominated era, and we are here today, which lies in the dark energy dominated era of our evolution of the universe. And cosmology is just the study of universe on large and small scales. Okay, so today the universe is constitute. So the contents of the universe are as shown in the pie chart here. So major portion of the universe is covered by a constituent called dark energy, which is a mysterious form of energy, which we are not. So this has been studied. It's been studied since several years, and the exact nature of this energy, this component, is still unknown. Then the second major component is the dark matter, and the third major is the ordinary matter, which is basically the atoms and other matter which we see all around us. Okay, with each constituent there is an associated energy density, and when we normalize this energy density, we get a parameter omega, which is called the density parameter, we would say. And so the sum of all the density parameters of all the constituents of the universe should always be equal to 1. So these are the dark matter, ordinary matter, lambda is the dark energy, and this is an extra component which is K, which is the curvature. This is not shown in the pie chart because to our knowledge, there is no curvature component in the universe today. Yeah, that means the universe is flat. Okay, let's come to the curvature of the universe. So this is a concept associated with the general relativity. And we just, for this talk, we just need to know that a flat universe, meaning zero curvature, this means that the omega k, which is the curvature and energy density parameter, is zero. For open universe, omega k is greater than zero, and closed universe, it's less than zero. And we'll be dealing so mostly with the open universe, which is the omega k greater than zero, so that we will have to deal with curvature of the universe in this topic. The next introductory slide is of cosmic microwave background. So this is just a background radiation, which is formed due to some early cosmology process leading to the era of recombination. So the recombination here is just uh, when the charged electrons and protons bound to form electrically neutral hydrogen atoms. And so this is as we speak. So as I have also told in the previous slide here, this is an evolution with time, right? So our universe has evolved with time, and if we go back in time, we cannot see anything beyond this surface with the resources available to us. So this image has been taken by the Planck satellite, which has studied CMB extensively. And this shows the temperature anisotropies, which we'll be dealing with mostly in the CMB at full resolution. So the temperature distribution at this surface, but as you can see, it is not isotropic, it is different at different points. And so we can calculate the anisotropies in the temperature distribution. Let's move ahead. So, okay. So this is a brief summarized timeline of the universe. So we are here today, and the universe started here. So this is the Big Bang. There was some initial process called inflation. That is a rapid expansion of the universe that led to some early universe processes. And then finally, this is the surface, which we just saw in the previous slide, which is the cosmic microwave background. And after quite a long time, we are here, which is the era dominated by the dark energy. And as I said at the very beginning, that our universe is in the state of accelerated expansion, and we postulate that dark energy is the cause for this acceleration of the expansion, right? So coming to the model that I have studied in my work, in my master thesis. So this model is defined by the Lemaître-Tolman-Bondi, which is LTB spacetime metric. And this is an exact solution to the Einstein field equations in general relativity. And okay, so this model is spherically symmetric and radially inhomogeneous region of the size of order 3 gigaparsecs, so which is pretty large, and it is surrounded by a flat homogeneous universe. So in this figure, in the background figure here, I just put it to visualize this model a bit, so that it becomes easier to visualize this model. So the gray area you see here is the spherically symmetric and radially inhomogeneous region. So the matter distribution is not the same at all points here, but outside this region, there is the flat homogeneous universe, which is also the case in standard cosmology. And this, so the one important factor I forgot to mention about is that in cosmology, there are two basic assumptions with regarding the universe. First of all, the universe is homogeneous, and secondly, it is isotropic on large scales, both on large scales. So on large scale, if we so the homogeneity means at large scale we can find the structure of the universe to be same at any point of the universe. Okay, and in isotropy means that if we look in any direction, the universe appears to be same on large scales. So in this model breaks the first assumption of homogeneity, so that this is a large region where there is, if we look at some point, then we won't see the exact same thing as if we see at some other point on large scales, of course. So 3 gigaparsec. So this is a radius of 1.5 gigaparsec, and it is pretty. So it's not a very small, even a little small distance measure. Anyway, so as I said in the earlier as well, this is a local void. That means the observer, which is denoted by the star here, is located inside the void region, and it is at some distance from the center of the universe. So because this assumption of homogeneity is violated here, this universe has a special position, which is the center of the universe, and yes, so observer is located at some distance. I was going to make one more point, but I seem to have forgotten it. And anyway, moving to next slide. So as I will be describing the matter density profile in this kind of universe. So as you can see, this is the omega m parameter, which is the density parameter for matter present in our universe, and this is equal to 1 in the flat homogeneous part of the universe, which is the white part. As expected, that is, the sum of all the constituents should be 1, right? So there is only one constituent present here, which is matter. And so wait, let me, if you see this, so this is the dark energy dominated era, which has started only some time ago. But some time is a lot of time in cosmology. But so the time when this region starts, so time when the dark energy is dominated, has dominated all the other constituents, that is when we replace the dark energy with we replace the dark energy with some other constituent called the curvature of the universe. And you can see that the matter density in the inside region of the void is less than 1, so that there is also some other component present, which is curvature, and the rest of the portion is occupied by the curvature density. And since this is a profile only for matter density, I have not denoted that here. And the condition of all the constituents summing to 1 still remains valid. Also inside the void, omega m is approximately equals to 0.25, and omega k, which is the curvature density parameter, is approximately equal to 0.75, which is the remaining part here. And outside, it's just that there is only one constituent called matter. One constituent matter, which sums up to 1, and omega k is 0. So there is no mention of dark energy here, because this model has basically replaced the dark energy with curvature density. And as opposed to dark energy, we can know the geometry of the universe. It is straightforward as compared to the dark energy, to finding the nature of dark energy. We'll see why we study these kind of universe. So at the very beginning, these inhomogeneous universe models were introduced to replace the unknown dark energy component of the universe. Okay, so it's difficult to study dark energy, and if there is some other component that can replace the dark energy, and also explain the accelerated expansion of the universe, for which the dark energy was introduced at the very beginning, then we can make things easier. So these models can actually explain the accelerated expansion of universe, but not in a very satisfying way. So we'll see why. So if we look at the CMB observations, and if we fit this model in the CMB observations, then there are studies concluding that the observer should be placed very near to the center of the universe. So this requires in general a very large fine tuning, and it is in disagreement with the inflation stage of the universe. So at the very beginning, before the CMB and after Big Bang, there was a phase called inflation, which is just a rapid expansion of the universe. And this model is not in agreement um, with the inflation phase of the universe. The second disadvantage of this model with regarding to the CMB observations is violation of the Copernican principle. The Copernican principle states that we are not present at any special place in the universe. Okay, but this kind of universe, as you have seen, this kind of universe has a special place called the center of the universe, which is not in general a reality. So this also violates the Copernican principle, and we do exist at a special place if the observer is to be placed near the center of the universe. Then the second set of observations that we can look at are the kinetic Sunyaev-Zeldovich effect observations. So let me explain briefly what the kinetic Sunyaev-Zeldovich effect is. So first of all, Sunyaev-Zeldovich effect, which is the SZ effect, it's just the distortion of the cosmic microwave background radiation through inverse Compton scattering by high energy electrons in galaxy clusters. So in which the low energy CMB photons coming from the CMB, of course, receive an average energy boost during collision with the high energy cluster electrons. So there are in the path between the last scattering surface and the observer, there are several galaxy clusters, and these cause the Sunyaev-Zeldovich effect, which is just the energy boost for the CMB photons. And kinetic Sunyaev-Zeldovich effect is just that when the clusters are moving with some velocity, bulk velocity, there is we have to account for that velocity as well. Anyway, so these observations are so we allow an extra freedom from the non-constant bang time. So the bang time is the time of Big Bang basically, and if we assume it to be non-constant and varying with some parameters, it allows extra freedom, and which is sufficient for some observables individually. So some observables like CMB observations, etc., etc. So individually they are okay, but to constrain them simultaneously, these are so this model seems to be insufficient, and hence these kind of observations are strongly constraining for the parameters. And so overall, using these the CMB observations and the KSZ observations, the model was ruled out using in these papers. So ruled out as a replacement for dark energy. So we came to the conclusion that we cannot replace dark energy completely by another constituent called the curvature of the universe. So why do we study now? Right, there's the obvious question now for the rest of the talk. So as I said, the standard model of cosmology has an underlying strong assumption of homogeneity in space on large scales, of course. In order to satisfy this model with the observations of the sky, it becomes crucial to test this assumption of homogeneity. Okay. Sorry. So this model helps us to test the assumption of homogeneity. Also, by the existent knowledge of the large scale structure of the universe, we are aware of the existence of voids in space. So voids are just some empty regions where there is a scarcity of matter. And we know by the study of large scale structure that such voids, such regions exist in space. And is there like maybe there is some way that the existence of these voids can distort the CMB measurements. So we can use this model, we can use this study to also check how the observations are affected by the presence of large scale voids. So the object of interest in the whole talk would be the photon trajectories from the CMB, from the last scattering surface. So let's see how they are calculated. We want to calculate the exact photon trajectories from the CMB using the model that we have and using the knowledge we already have from the observations. So first of all, we have this structure of metric from the LTB metric, and the whole structure is not important at all for this talk. You just need to understand that we can define any kind of space-time metric by equation like this. So, and using Einstein field equations, we can solve the metric for the parameters, for the unknown parameters that are present in here. For example, one of them is this capital R, which is a function of R and time, small r and time, and small r is just the co-moving distance of the universe in the universe. And we can also, okay, so first of all, we input the matter and curvature density parameters, which is alpha and beta. And it's an interesting note here that the important difference between homogeneous and inhomogeneous models is that the functions in the inhomogeneous models are dependent on small r, which is the radial distance, the radial coordinate, as well as time. So in standard model, we don't have the dependence on small r. It's only the functions of the parameters of the universe are only time dependent. But in inhomogeneous models, it becomes necessary to also include the dependence on uh, radial parameter, because it's not the same everywhere, right? So using Einstein field equations and the metric and the self-set matter and curvature density parameters, alpha and beta, we can find solutions. So these are parametric solutions. So we find the solutions for the capital R as a function of R and eta, and also the time, the physical time t, as a function of small r and eta, where eta is just a conformal time parameter. The equation, don't worry about it. It's just using some substitutions, we substitute this equation to make the structure of the solutions easier for calculations, for further calculations, right? Moving on, so from solutions, we input the solutions in the photon geodesic equations, which also come from the general relativity. And using the ray tracing method, we have such solutions for the CMB photon trajectories. So the lines here you see, the curves you see here are just the CMB photons tracing a path coming from CMB to the observer. The observer is placed, so the red cross here is the center of the universe, and observer is placed at some distance from the center of the universe, right? So the photons coming from CMB converge at the observer position. So looking at the large picture, this is how it looks like. So this is the last scattering surface where the CMB emits the photon, right? So where the CMB photons are emitted. These photons follow a blue curve called the geodesic. Of course, these geodesics are obtained by the geodesic equation, which I talked about, sorry. So these geodesic equations, they can be solved to find the geodesic of the any photon coming from the CMB. And as you can see, due to the presence of the void, there is a kind of bending of the geodesic, of the path of photon, right? So we will account for this bending in this talk, and why is it like, what are the contributions to this bending, and what is the amplitude of that contribution, etc. So and now the quantity that we want to look at to calculate the bending. So what do we look at in the photon trajectory? So photons coming from the CMB, what do we look at that? So we look at the CMB temperature anisotropies, which are the anisotropies in the temperature distribution of CMB. So the total anisotropy of the CMB, temperature anisotropy, sorry. So there are two kinds of anisotropies, also the polarization and the temperature. So we'll only consider temperature here. The total temperature anisotropy can be written as expansion of, it can be expanded into mainly 3 factors, but there is also additional 4 factor, which is non-relevant here because it's very subdominant with respect to all the other 3 factors. Okay. So first is, you see from starting from the left, first is the primary anisotropies, which are only due to the CMB intrinsic anisotropies, this contribution. And the intrinsic anisotropies means that it is due to some early universe process in the recombination era, and we can so the causes for these kind of anisotropies is in the inflationary phase of the universe. So we don't talk about that much, but we just need to know that there is certain contribution which exists in the CMB intrinsically. The second contribution, it comes only from the void, from the presence of the void. So the observer is present at some distance from the center, and due to that, there is a bending of the photon trajectories. So as we saw in the previous slide, so just due to the observer being present at some distance from the center, there is this bending. If the observer was present at the center, then the photons would have followed this yellow dotted line for its trajectory, right? So there would not have been any bending. So this second term only accounts for the bending of the trajectories due to the presence of void and the off-center position of the observer inside the void. The rest of the 2 terms are the secondary terms, which are when expanded in the first order of lensing and radial modulation. So these terms are due to the combination of the first 2 terms. So due to combination of CMB intrinsic anisotropies and due to the presence of void, right? So this is a combined effect, and of these we'll be focusing mainly on the lensing-like displacement because it is much dominant with respect to the radial modulation. So this is the main topic of the study. So main objective of the study. So as a reminder, I just want to remind you that there are, so this is the big picture model of the deflection of the geodesics of the photon trajectories, right? And so there are 2 models which I'm considering, which I've considered for this work. So model A and model B. Model A is just a smooth transition from a low matter density to high matter density, and model B is kind of a discrete transition, so that so we need to so the matter, we can say that the matter inside, which was supposed to be inside the void region, is accumulated at the edge of the void. So these does not these over edges do not cause any large effects in the study, but we just need to know. Okay. So okay, first of all, there is this parameter which measures the deflection of the photon geodesic, right? The photon trajectory. So the parameter is gamma, and we will study the lensing-like effect using only this deflection parameter. So in the specific geometry chosen, the lensing-like deflection only has gradient modes. The deflection is, as I said, is denoted by the parameter gamma, and of course there is a lensing potential associated with this deflection parameter. Okay. More details on it can be found in this archive publication. So let's carry on to the calculation of 2-point correlation functions using this lensing potential in the harmonic space, spherical harmonic space. So firstly, the definition of correlation function. So the 2-point correlation function is defined by the average of statistical average of the any quantity. So here we are taking the quantity to be temperature and isotropy in the CMB. So N1 and N2 are just any two directions. So we take theta at in some direction and theta in second direction, and we average all over the space. Secondly, so this temperature and isotropy can be broken down into as spherical harmonics. Then we can calculate, so in the spherical harmonic space, we can calculate this 2-point correlation function, which is f. And for so just for information, for statistically isotropic random field, any random field on a sphere, this function is a diagonal matrix, right? But as as our space is not statistically isotropic, this function would also contain off diagonal elements. Well, the structure becomes so the equations become more and more non-trivial after this, but the main thing to know is we have a definite analytical equation of the 2-point correlation function for our model. So we just go ahead and calculate the correlation function. And this function matrix has a complex structure. So we'll only see for the modes m and m prime equals to 0. So okay, wait, where is this? So we have f of L, m, L prime, m prime, and we set m and m prime to 0. So as you can see on the y-axis, this is the correlation function normalized with respect to the diagonal elements, right? And the x-axis on the both of these graphs are the number of diagonal elements. So we see how the structure varies as we go more off diagonal, right? So if we consider the 20 off diagonal elements, the structure, we will look at the structure between 0 and 20, and 0 corresponds to the diagonal element of the matrix. And as I've said, the model A and model B are two models that have the two toy models that we are considered for this study. So model A was the one where, okay, for a quick recap, model A was the one, there was a smooth transition from inner region to outer region. And model B has a kind of strict discrete transition, right? So coming back to the graph, so you can see that the graphs, first of all, the important point to be noted here is the function is rapidly decreasing with the off diagonal elements. So for the calculation, it's helpful for the calculation of signal to noise ratio, as I will show in the further slides, that we don't need to consider too many of diagonal elements. So we can only stop at, for example, of diagonal element of 20, and the same here. So because the order is quite low here, so 10 to the power minus 5, 10 to the power minus 6 difference, right? And here even lower. And okay, so moving on, so let's discuss the cosmological implications of the 2-point correlation matrix. So first of all, this matrix basically in the LTB model, we only look at the geometrical contributions of the lensing basically, right? So the lensing is quite a major contributes quite so the contribution of the lensing, sorry for the contribution of the lensing is quite dominant with respect to the kinematical contributions which we study in the standard model. So the important notes about the so the 2-point correlation function is that it always has non-vanishing diagonal elements. That is, the first element of these graphs is non-vanishing. Okay, here it's normalized, so it's 1. But it has some value. And also the off diagonal elements of this matrix are excited. So for a given, for a linear order in lensing, we see that the correlation exists among all neighboring multipoles because the function is continuous. So the function is continuous with the off diagonal elements. So we at linear order in lensing, we see that there is correlation among all the neighboring multipoles. Let's keep it aside and look at the standard model. So for the standard model, we focus on the kinematical contributions which come from the observer velocity with respect to the rest frame of the cosmic microwave background. So every body in the universe has some velocity. So the galaxy, the solar system within galaxy, and the Earth. So we only have the CMB frame as a rest frame. So which is the basic reference frame for our velocity, and we can so our velocity, the Earth's velocity or the observer's velocity, has been calculated with respect to this rest frame using the observations we have until now from Planck satellite, from WMAP satellite, etc. And if we calculate a similar correlation matrix, so if the way we have calculated the correlation matrix in the LTV model, if we calculate a similar correlation matrix in this case, in the standard model case, we always get vanishing diagonal elements. So you see that's a very important difference between the LTB model and the standard model. Moreover, at, for example, linear order in the velocity of the observer. So we call the velocity boost velocity. And if we calculate the temperature anisotropies at linear order in this velocity, we see that the correlations exist only among L and L plus 1. If we generalize it to the order of beta to the power n, beta is the boost velocity here. If we generalize it to the order n, then we see that the correlation exists only among L and L plus minus order n, the nth diagonal element, off diagonal element, right? So also, unlike the LTB model, the correlation does not exist among all the neighboring multipoles. So only with some neighboring multipoles, depending on which order of velocity we expand the temperature anisotropies in. So this here, as it is very apparent, it's an important signature of the LTB model. So the geometric effect which we are looking for in the CMB observations, if we see the correlation in the correlation matrix, if we see that the correlation exists among all neighboring multipoles, then this is the signature of the LTB model, or in general an inhomogeneous model, right? So using the correlation functions, I calculated Fisher forecast, Fisher analysis, and I calculated the signal to noise ratio for both the toy models that I've considered, model A and model B. The blue lines here are for model A, and the red lines are for model B. And the dotted lines here are for the signal to noise ratio, including the noise of the Planck satellite. So the Planck instrument has some instrument noise of its own. And if we include that noise, we get the dotted lines as the signal to noise ratio. With respect to the x-axis is the multipoles, the number of multipoles that we can calculate up to, right? So for Planck, for the Planck satellite, unfortunately, it does not it is not able to calculate at multipoles higher than 2500. But if we have in future, if we have a good instrument which can calculate at higher multipoles with good sensitivity, then it is possible to detect these kind of these kind of models, basically these kind of signatures in the two-point correlation function. And so we are moving towards the end of my talk. So it was just meant to be an introductory talk. If we go in the details, there is a lot of things. So let's so for now sorry, I don't know that one. Okay, so for now we are working on the same project, which is just the application of the framework, the whole framework developed to some more so wide class of matter dominated LTB void models. So these models can have different sizes of the voids, ranging from gigaparsec to even smaller sizes. Then it can have different position of the observer, which is located from the center of the universe. And also we are studying some models which include the lambda, which is the dark energy, cosmological constant, which represents the dark energy constituent. So as in the beginning of the talk, I told that these models are not valid as the complete replacement of the dark energy. So we can just add the dark energy component and check for the homogeneity of the universe. So which can be considered as a more realistic model. And also there is then comparison of results with limiting cases of empty spherical voids embedded in the flat FLRW regions. So the similar kind of voids, but so for example, here all the matter was almost accumulated at the edge of the void. So we can compare with different kind of models where all the matter is concentrated at the center of the void, which is basically a black hole, Schwarzschild model. So this is still going on, and we can move on to the conclusions or summary of the talk. So we saw that how the LTB model is designed and constructed, for example, and also how we can calculate the photon trajectories in this model. So the CMB photon trajectories. Then considering the temperature anisotropies that exist in the cosmic microwave background, there are three components, and we focused for the most of the talk on the lensing-like deflection, which is a second order contribution to this temperature anisotropy. Then using the lensing-like deflection angle, we and via the lensing potential associated with it, we calculated a correlation function, and also saw how the structure of the correlation function uh, can help us differentiate this kind of model from the standard cosmological model. And finally, using Fisher analysis, we calculated signal to noise ratio, and we can obviously get a clean signal at some higher multipoles if it is observable by a Planck-like instrument, but with higher sensitivity. So that would conclude my talk. Thank you very much for your attention, and thank you very much for coming. If there are questions, then I will try to answer them now.
Thank you, Viraj. It was really interesting. Okay, so let's move on to the question answer session. If you have any question, you can either raise your hand or write it in the chat box. I will read it out to Viraj. So, are there any questions?
Hello, can you hear me?
Yes, sir.
Yeah,
Go on.
I have a few questions. That is okay. So you're assuming that uh, locally we are in a void that is an under density, but I mean it could have been an over dense region as well. So in that case, what?
So we chose the underdense region because the probability of existence of overdense regions in at such large scale, it's quite low. So right, I mean, if we look at the large scale structure, there are uh, three kinds of elements. So there are voids, which is just the absence of matter. There are filaments, and there are sheets in the
Yes.
last picture. So I think there are hardly any regions where, like on large scales, there are hardly any regions where there is higher matter density than normal. So we can postulate, we can maybe estimate that there are regions where, there is a very large scale region where there is in general lower matter density because uh, there we also have the another constituent in the universe, which is the dark energy. And as I said, this model was initially designed or studied to just replace the dark energy component uh, with a curvature component. And if it is replacing the dark energy component, then the curvature component, the omega k, would be positive, right?
Right.
And omega k positive, it's an open universe, which means it's a lower matter density universe.
Okay, okay. And my next question is, so in both of your models, I saw that there is a specific length scale that you're talking about, that is 1.5 gigaparsec.
Mhm.
So why are we choosing that?
This is basically just the scale where the dark energy comes into play. So
Okay,
dark energy became dominant at certain point in redshift, right?
yeah.
So where the void boundary is defined, sort of approximately, of course.
Okay, 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 okay. And my last question, that is, so you were talking about lensing, and then you showed us some correlation plots. Can you take us to that?
The plots, these
Yeah,
ones.
yeah, this one. Okay, I mean, from the data of Planck and other such CMB surveys, what I've seen, this correlation between the shear or the convergence. So, like, are these related to like those shear correlation or shear, sorry, convergence correlation, those kind of things?
So that is for the gravitational lensing, right?
Yeah, and this is,
This is for the lensing due to the void boundary, due to the low matter density. So, I mean, gravitational lensing can be due to the large number of galaxy clusters, galaxies present in the line of sight of the CMB photons. But this is more of a geometrical effect.
yeah, I mean, in general relativity, geometry and gravity are like two sides of the same coin, right? So,
Yeah.
so I mean, there shouldn't be any difference between the two forms of lensing.
Okay. Could you repeat your question once, like the main question?
Yeah,
You,
what I'm saying is, how are these correlation functions related to the, uh, I mean, the correlation between shear or correlation between convergence that we see from the data of Planck. Uh,
Mhm.
those, like, are they related or they're not?
uh, I am not very sure about this, so I
Okay,
should
okay,
comment
okay,
that.
okay. Okay, thank you so much. Wonderful talk. Thank you.
Thank you very much.
Okay, next we have a question from the chat from Navunita Das. She asks, how do we measure the contribution of each term, that is intrinsic anisotropy due to the void, in the temperature anisotropy from observation?
So, well, the intrinsic anisotropies, we can just, like for the purpose of calculations, we can just import them from the class or CAM codes developed, right, for CMB. So these are just using the observations directly, the CMB observations directly, and then the second, the non-stochastic contribution, it is, well, it is studied before, but okay, wait. So this is basically the contribution due to off-center position of the observer, right? And we just, in this case, we just we just measure the redshift. Uh, so for example, sorry, uh, I mean, so there is this factor, this uh, parameter for measuring the lensing light contribution, right? So similarly for the non-stochastic contribution, there is a parameter, the redshift distribution of the last scattering surface. So we calculate the redshift at which the photon was emitted at the last scattering surface. This has a uh, distribution which is a bit off from the sinusoidal distribution, and uh, using the redshift, using the redshift distortion, we can directly calculate the temperature distortion, the temperature anisotropy contribution in this respect. So in the non-stochastic. So it may be not very clear from what I'm talking, and I also don't have, unfortunately, the equations and the graphs showing this, because this was not the main title of my main object of my study. But maybe you can find this in this one probably. Yeah, maybe this archive. So if you look it up, then maybe you can find the main equation which they use to calculate this contribution. And for the final, as I've said, it's just so using this parameter gamma, which is the lensing deflection angle. Does that answer your question?
Yes.
Okay,
Okay, thank you.
thank you.
Okay, so next we have Shopurna. Shopurna, please unmute yourself.
Yeah, so I had a question. I had basically few questions. One is, you showed that you are choosing two models where one is a smooth transition from 0 to 1, and another is sharp transition. So I was like bothering that yes, here. So you see in the small region where there is phase transition,
Mhm.
here we are considering only omega matter and omega k, right? I mean the curvature and matter.
Uh,
So
right, in model A.
yeah, in model A, right?
Yeah.
Okay. So that's not in model B.
No, in both models actually. Yeah.
Yeah. So if that, then uh, in the once you leave the void in the small region where we are leaving the void, there omega m goes more than one, and so to keep omega m plus omega k equal to one, I need the curvature to go negative. I mean the
That
so
is true.
right. So
That
so
is,
right. So why is that? Like I mean, why are you choosing a model where there is a steep change in curvature suddenly? I mean, it's changing its entire structure, and then
yeah, this change
so
was not actually the design of the model, but uh, just to sorry, just to conserve the total of the energy density parameters. We need, so this is a very this is supposed to be, so this is obviously a not a very uh, accurate description or sorry, accurate model figure, but this is a very small window where all that matter is accumulated, and
right,
this is
right.
due to the the negative omega k. uh, the photons are bent in their trajectories, right? So there was this bending, if you remember.
Oh, so that graph where the photons were actually curving was due to this.
Yes,
Okay, okay.
this one. So you see there is small bends at the edge of the universe, edge of the void,
Yeah.
sorry, and these are mostly due to this negative curvature omega k.
Okay. Okay.
I mean
So,
the
so
yeah.
yeah. Yeah, continue.
No, go on. I mean, it's just that inside the void, these trajectories also appear to be pretty straight, right?
Yeah, right, right.
It's
Yeah.
not the effect of positive omega k, and it's only the effect of negative omega k that there is some bending in the paths. Yeah, but go on with your second question.
Yeah. Okay. So, and another one is a basic one. So that you mentioned that your inhomogeneities cannot has some problem with inflation and all. So like at least the inflation part, could you like what problem is there with? I mean, is it the one is it the one that in due to inflation, the one that explains that we do not have an inhomogeneous is because there was inflation? Is it that one? Right.
Yes, exactly. Not exactly. So we have the intrinsic CMB anisotropies from the inflation part, right? Uh, which are present intrinsically in the CMB. Those are generated because of the inflationary phase of the evolution. and the fact that the observer, the prediction that the observer must be placed very near to the center of the universe, that means that the higher order anisotropies are, uh, the higher order than dipoles, they are not in agreement with the CMB intrinsic anisotropies. Or
Okay.
maybe you mean something else by your question, maybe.
Uh, yeah. And I mean that this just like maybe a naive explanation of why is it in disagreement with inflation? So like why is inhomogeneous in disagreement with inflation? So
Because yes, I mean, basically the fact that we cannot match the CMB temperature anisotropies uh, from this model with uh, with the ones which are observed directly from the Planck. And the ones observed directly from the Planck, that is the primary anisotropies, they are due to inflation. So that's why it's just that it's a conclusion that it does not agree with inflation as well as the standard model.
okay, okay, thanks. Yeah, nice talk.
Okay.
Okay, next we have a question from Debayon Paul. He asks, can you please elaborate on what is the role of the density parameter which is showed in one of the slides?
Which density parameter to you? This one?
Debayon, if you can unmute yourself.
Yes, yes.
So this one
The,
just has
I
uh,
wanted to know the basic concept of that density parameter actually.
yeah. So this actually this parameter is not. It mostly comes from the. Uh, it's a very different branch of study of physics, the GR, and it's basically the associated with the. I mean, I was even confused like how to explain the curvature of the universe to without involving GR, but yeah, it's just that you can understand it as the remaining parameter which is other than the matter and dark energy. So the whichever one is remaining, and if the sum of the omega dark matter, omega ordinary matter, and omega lambda are not equals to 1, then the remaining contribution can come from the curvature of the universe.
Okay, and those percentage which are there in this pie chart. So like, is this percentage fixed, or it may vary with uh, different time span or like that?
Yeah, so it does vary. So these percentages are only shown for the current present time.
Okay,
And
thank you, thank you.
so as I have shown here, so this can help us create different pie charts for different times in the universe, in the history of the universe.
Okay.
Yeah. Okay.
Okay. Next, we have a question from Gorima Rajguru. She asks, what other areas can Fisher analysis can be applied to?
I mean, Fisher analysis is basically applied to calculate any for forecast. I mean, I only know of mostly the cosmological applications. But if you mean other areas like, yeah, maybe even in simulations, whatever kind of simulations, if you just in general want to predict the amplitude or the power of the contribution of any particular parameter, then you just create a Fisher analysis. You do a Fisher analysis with respect to that parameter, and you can estimate the usefulness of the parameter. I mean, maybe I'm not answering it perfectly, but yeah, I mostly know about the applications in cosmology. So, in galaxy studies, for example, uh, it is used to estimate the sigma 8 parameters which are related with the large scale structure, and also dark energy parameters, which is W. If you only know this if you study cosmology, I mean, it's we would have to go into several details to explain that. But yes, uh, it's just a normal analysis to predict the usefulness of a parameter or a, yeah, any function.
Okay. She says thank you and nice talk.
Thank
Are
you.
there any more questions? I don't see any more. Okay, if not, then I have a couple of questions. So, what is this black straight line in this plot? What does that signify?
This just is a certain threshold that after which we see a cleaner signal. So the
Uh,
signal noise is comparatively larger here, right?
right, but the threshold depends on the instrument.
There,
What instrument I'm measuring?
there is no concrete threshold that I've defined. It's just uh, it's like after, for example, a signal to noise ratio of 10, then we know that the noise becomes gradually smaller and smaller after this.
Okay,
So for 100, then for a ratio of 100, the difference between noise and signal is around 10 to power 2, uh, the 2 powers, so right, 2 orders of 10.
I see.
So just I mean, it's a very rudimentary prediction right now, and we don't have any concrete data from any surveys. So this is just with respect to Planck, and also the signal to noise ratio, including the Planck noise, reaches above this threshold. That means there is a possibility to get a even cleaner signal.
Okay,
Yeah.
okay. I have two more questions, but there is another question in the chat, so let me first get to that. So Navonita Das asks, maybe I missed this part. Why is there no bending of photon trajectory due to void when the observer is at the center?
Due to void. Yeah. So okay, in this figure, if you see, if the observer is at center, then there is naturally no bending for any photon trajectories coming from any direction. So if the observer is here, for example, not at the center, then the photon trajectory coming from this along the z-axis would not have any deflection, but the photon trajectories coming from the x-axis would have a clear deflection. So if the distance between center and void, center and observer is reduced, then there will be reduced deflection of all the trajectories, and at the center, essentially, it will be zero. I
Okay.
mean,
Does that answer your question?
just a geometrical reason.
Okay. Okay. So if there aren't any more questions from others, then let's get to my two more questions. Um, I saw some dips in the correlation function plot.
Okay.
So what are those
So
dips?
these are just a sign change. So this is the absolute value, and whenever the signs change, so it's like a wavy structure, and uh, whenever the signs change, it goes to some, and then you can understand, right?
Okay, I see.
So okay, I don't have the original plot like without absolute value, but without absolute value, it's like this wavy structure, so
Okay.
waves, and whenever the signs change, there is a, well, we cannot predict, we cannot see that in the original structure of the function, but yeah, when we take absolute value, there it creates dips like this.
Okay.
It's nothing significant though.
Okay. Okay. And so for my last question, you said that the omega m parameter or the curvature density parameter of curvature varies with the positions, right?
Yeah.
Okay. So will that create any difference in structure formation of the universe?
Uh, I mean
Yeah. So we know that the density parameter in standard cosmology, the density parameter just varies with time or redshift, not with different positions, right?
Yeah.
Yeah.
So
So yeah. So if it varies with position, then will there be any difference in the structure formation of the universe?
I mean, so I think for structure formation, basically the perturbation theory still remains the same, right? It's just that the background universe is the structure of the background universe is changed, but the other even the structure formation would remain same.
Oh,
Maybe it will differ a little bit in this region where there is a change of the omega m. But so if you see here, the attempt of this model B here is to create a homogeneous universe inside the void as well, right? But it's homogeneous, but with the contribution of omega k, the,
right.
instead of dark energy. So even if the dark energy is present, I mean, yeah, so the structure formation happens before that, but yeah, I mean, it won't change. The simple answer is no.
I see. Okay, I don't see any other questions. So let's thank Viraj for the wonderful talk.
Yeah, thank you for attending.